the last way we're going to look at in this chapter to calculate enthalpy change is using what's called standard molar enthalpy of formation. Now, this essentially is going to look like you looking up values from a table, and giving the enthalpy equation, you are going to be able to calculate the delta H. Now, some things you need to know. If a compound is formed from its elements, we're going to actually call that the enthalpy of formation for that compound. So that's what you're going to be looking up in the table, is these values that are obtained from the formation of the compound from its elements. Now, standard conditions are important. These enthalpies of formations are measured at standard conditions, which is going to be 1 atmosphere pressure and 25 degrees Celsius or 298 degree Kelvin. And the standard enthalpy for everything measured, which is going to be indicated using a degree sign following the delta H, is going to indicate that it's measured in its standard state, so that 1 atmosphere pressure, the 25 degrees Celsius.
Okay, so standard enthalpy of formation of a compound. Delta HF is the enthalpy change for the formation of 1 mole of a compound with all substances in their standard states, which means the reactants are going to be elements and the product is going to be 1 mole of a compound. And because elements are arbitrarily given an enthalpy of formation equal to 0, when the compound is formed, the energy that's evolved or absorbed is called the standard enthalpy of formation, as long as it's at standard conditions.
Now, the equation that we're going to use using the standard enthalpy of formations that you'll be looking up on a table is that the enthalpy change for the reaction, which is the RxN, is equal to the sum of the enthalpy change of formation for the products minus the sum of the enthalpy change of formation for the reactants. Now, again, this is going to be at all standard states, so there should be a little degree sign here. So go ahead and put that in. This sigma, that's a summation sign, and it just means sum. So you're going to add all the products' enthalpies of formation together, and you're going to subtract it from all the reactants' enthalpies of formation. Be sure you keep track of signs. So if it's given as an exothermic enthalpy of formation, make sure you include the negative sign in the equation when you actually go to solve.
Okay, now I'm going to show you why it works. Let's take this as an example where we have methane gas reacting with 4-chlorine to produce a carbon tetrachloride plus 4HCl. We can actually write this as a sum of 3 formation reactions. So let's start with the carbon tech, which is the product. We can write a heat of formation reaction for carbon tetrachloride by putting down solid carbon plus 2 diatomic chlorine gas yields 1 carbon tetrachloride liquid. And the delta H of formation for carbon tetrachloride, because this reaction represents a formation reaction, all you have on the left are elements and you have 1 mole of the product on the product side. The heat of formation of carbon tetrachloride is negative 139.5 kilojoules. And again, that can be found in the table. For the second product, we have 4 hydrogen chloride gas produced. So on the left side, we're going to have 2 hydrogen gas plus 2 diatomic chlorine gas yields 4 HCl gas. And notice that hydrogen is found as a gas in nature, which is why you give it as a gas, and chlorine is a gas in nature, which is why that's written as a gas. And they're also both diatomic. The reactant, CH4, we can show that as the reverse of a formation. Oh, the delta HF, sorry. Let's see. The delta HF of HCl is negative 167.2. And we have to multiply that times 4. So it's negative 668.8. Okay, so the CH4, which is on the left, we're going to write that as the reverse of a formation reaction. So we're going to have CH4 gas yields carbon solid, which is the standard form of carbon, plus 2 of the diatomic hydrogen gas. And that reaction is the opposite of the heat of formation. The heat of formation of methane gas is negative 74.8. So for this reaction, my delta H would be positive 74.8. Now, according to Hess's law, if those three reactions added together give me the one I'm looking for, the delta H's added together will give me what I'm looking for. So if I add those together, you'll see that the carbon in the first reaction cancels with the carbon in the third. The 2 hydrogen gas that are in the beginning of the second reaction cancel with the 2 hydrogen gas in the third reaction. And we end up with CH4 gas plus 4 diatomic chlorines yields 1 carbon tetrachloride liquid plus 4 HCl gas. Now, if we look at that in terms of the delta H's, the delta H for this reaction is equal to the heat of formation of carbon tetrachloride, which is negative 139.5, plus 4 times the heat of formation of the HCl, which is negative 668.8, the original value was negative 167.2. And we're going to subtract from that the heat of formation of the methane gas, which was negative 74.8. And because we subtracted that, we ended up changing the sign. And the value that you get, I should probably have a drum roll, 139.5. Okay, it takes me longer than that. Plus 74.8. Okay, so you end up getting negative 733.5 kilojoules. So rather than using Hess's law and writing out the 3 reactions and seeing how everything cancels, all you're really doing is taking the heat of formation of the products, multiplied times their coefficient, and subtracting the heat of formation of the reactants. So that's it for the different ways that we can.
So in this example, you have the thermite reaction. In the thermite reaction, we have iron 3 oxide reacting with 2 moles of aluminum to produce 2 moles of iron and aluminum oxide. So we want to calculate the standard enthalpy of formation for the thermite reaction. So we're going to, instead of using Hess's law and writing out each reaction, we are going to look up the heat of formation values from a reference table. Now the reference tables can be found in the back of your textbook. And using the reference table from the back of your textbook, I looked up the standard enthalpy of formation of the iron 3 oxide. And the standard enthalpy of formation is negative 822.16. So what I like to do is just kind of write that above the reaction to kind of keep track of what's going on. Now, aluminum is in a standard state. So aluminum standard state is the solid phase. So the standard enthalpy of formation for aluminum is going to be 0. Looking at the first product, iron, standard state is solid. So the standard enthalpy of formation for iron is going to be 0. And the last standard enthalpy of formation is going to be for the aluminum oxide, which is going to be a negative 1,669.8 kilojoules. Now, if you look back at the equation that I gave you previously, the standard enthalpy of formation is equal to the sum of the standard enthalpy of formation of the products minus the sum of the standard enthalpy of formation of the reactants. So plugging in the values that's given in the problem, or that I looked up from my table, I have a coefficient of 2 in front of the iron, so it's going to be 2 times 0, plus, because it's sum, the standard enthalpy of formation of the aluminum oxide, so that's a negative 1,669.8. So that's my product standard enthalpy of formation. And I'm going to subtract from it 1 times the standard enthalpy of formation of the iron 3 oxide, so that's a negative 822.16 plus 2 times 0. So if I add or do the math, I come out with negative 847.64 kilojoules. And significant figure-wise, I can only have one decimal place, so it's really negative 847.6 kilojoules.
And that's a lot of energy. If you've ever done the thermite reaction, I taught a chemistry camp one year, actually for a couple years, and we used to do the thermite reaction, but it's not something that should be done in a high school laboratory. This was under very good supervision in the university lab, because it's pretty explosive. Very cool, but very dangerous.
Okay, so that's the last way we're going to use to calculate standard enthalpy of formation. So let's just look at some important notable things you need to remember about enthalpy. One thing that comes up quite a bit when teaching this chapter is the enthalpies for reactions are sometimes given special names, which tend to make students think it means something different, but it really doesn't. One is the formation, which we just talked about, and this is when all the reactants and elements form only 1 molar product. We're going to indicate that using the delta H sub F. The other is enthalpy change for a combustion reaction, and that again is when you have something reacting with oxygen. Sometimes that's noted as delta H combustion, COMB.
You know, and another one is, when we did the calorimetry problem, we had hydrochloric acid reacting with sodium hydroxide. That's a neutralization reaction, so sometimes that's called the heat and neutralization, which is delta H, and then it would be NEUT.
Now, realize this doesn't change how you calculate them necessarily. So if you see that the delta H is given some sort of specific subscript, don't let that confuse you in your approach to solving the problem.
Okay, more notable facts. Equations to determine enthalpy can be rearranged to determine any of the components of the equation. For example, if you have the delta H for a reaction is equal to product minus reactants, and you wanted to figure out what the delta H of formation of one of the reactants is, you just have to rearrange the equation. This is just like algebra. It's manipulating equations. You have to remember that the enthalpy of all elements in their standard states is equal to 0. In your textbook, it's actually given. The elements are listed, but sometimes you go to a table of enthalpies and they don't have anything for the elements, and students get confused because they can't find them. Well, if they have enthalpies of 0. And the enthalpy of formation of the hydrogen ion is also equal to 0. The enthalpy of formation of other ions is not equal to 0, but for hydrogen it is. And that again is a standard reference. That concludes our chapter.
You are done with your first unit.
Yay! Test